table determinism, right?
Yes, correct.
All yours.
It's all. Oh, sorry. So, the motivation for this actually goes beyond this. This was its first trying to set a deterministic, repeatable form when using neural networks for later work, which is going to be about rule extraction. So in order to do that, we need the weights to be very well perfected, understood, of the noise that comes into the system, so that in later work, we can work with those much more meaningfully. So the two parts really there is repeatability. We'll see that, and there's an unexpected problem that will occur that we have to resolve. And I've provided source code at the back, so you can do this in your own systems as well. So you can have your own participation in this and do this for your own systems as well. Okay, sorry, I should just point out that this is my name here, which is Richard Rudd-Orthner, and my professor is Ludmilla sorry, Sadie Barbers. And I'm doing a PhD at the University of Sheffield. So this is basically the running order that we're looking at today. It shouldn't take too long to go through it, but essentially we'll look at some of the challenges for mission critical software, because my area that I'm particularly interested in is safety critical AI, and particularly training systems with intangible problems and then extracting the algorithms out, okay, which is rule extraction. Okay. There's been some developments in the area, mostly in the USSR, or Russian Federation actually, and then I'll explain our approach, and there's a couple of examples, and we'll summarize, and then we'll tackle this issue that will occur with repeatability. Okay. So the first thing really is just to consider that artificial intelligence is mostly, with neural nets, around about mimicking human abilities. But actually mission critical software is actually about being more than human. So what we're trying to do is embrace the two things together to increase that mimicking of abilities to be beyond human. So part of the developments in this area, and there are some papers cited in the paper, and they, maybe unsurprisingly, are mostly in autonomous scenarios. Some in the space, some in unmanned vehicles, etc. But other areas also are pertinent to this, law enforcement and so on. Anywhere that we're trying to increase our understanding or increase our ability of what we're trying to achieve with a neural net and machine learning scenario. Okay, so machine learning offers us an ability to create a generalized model. Philosophically, we can look at this that in the forward chaining or the predictive state of the neural network, it's a kind of a deductive reasoning. It has a model, and you apply data to it, and it gives you classifications or categories on the other side. And that's very philosophically Aristotle reasoning. But the point why machine learning has been so successful is actually goes back to 2,000 years beyond Aristotle, and a lot back from today, which actually is Sir Francis Bacon's reasoning method, which are inductive. And it's the backward chaining element of this that allows the machine learning to occur to form the generalized model. The conditions that we are particularly interested in with this is that the initial state, and to try and perfect those, we're going to talk about and demonstrate some initial state schemes. However, neural networks does actually form a problem, whereas it can create solutions which don't obey any laws of physics or any obeyed constraints. Actually, it's the focus of my PhD is either to create a neural network that is constrained or an expert system that can learn, and ultimately it will be a combined effect. And what we really want to get to then is, for the focus of this initial work, is we're looking at the initial state of the neural network and its training. So the approach. The approach was to take a very well understood, that people are very much familiar with, the hello world, with a NIST data set, which is handwritten text, and basically you put the pictures in one side, and it tells you the numbers on the other side. It's very well understood, and because it's very mature, what we wanted to do is demonstrate our research with this very well understood. It's implemented with TensorFlow, Keras, and NumPy, and the code is all respective of that as well. I will point out that this data set also gets bundled with that, so you can just demonstrate this and have a go yourself. Okay, and what we want to do is look at the measures of accuracy and loss and so on. Okay, and part of the work that we're going to look then is we're going to look at different initialization schemes that will vary between number value, number range, and gradient. The gradient seems quite important since we have stochastic gradient descent, so it might imply that that is something that might be of interest to us. So with those schemes, we're going to use a fixed constant value across the weights. We're going to use a ramp or a linear ramp across those, which gives us a variation in the ramps with a fixed gradient, and then a sine wave which varies the gradient across it. Okay. Okay. The limitations of this, of course, is that it is coupled to the implementation of that work, that is as the test case, which is the Hello World NIST data set. And what we may find is that some of this is actually maybe coupled to things like the activation functions that are used in layers, and also coupled to the generalization model. So the first thing I did was, get things out, and this is the baseline software diagrammatically, and essentially there's 28 by 28 pixels, text in monochrome. It is flattened. All that means is it takes the image, makes it into a big long tensor or array, and then it applies it to a dense layer or a perceptron layer, if you like, and a dropout layer, and then a final dense layer for doing the categorization to say this is number 0 to 9. Okay. So that's what the baseline code does, and again in the paper that is provided too, so you can literally start from that, and the paper will prompt you to where to replace the code as we go through the experiments. Okay. What we did, of course, was run that, and we got some variation in the results every time we trained it. And that was quite surprising, but what probably we should consider from that is that there is random numbers being applied into the initial state. So one could imagine that the first thing we'd want to do is seed the random number generator. So we seed the random number generator, and this is the code, and again it's in the paper as well. Unfortunately, the variation continues, which was a bit surprising. There'll be another reason. The paper hypothesizes for some of these reasons, and what I haven't done is put an ICE controller onto the processor to absolutely equivocally root down the problem for this, but I do have a solution to it and a rather convincing argument. I haven't actually debugged it with an ICE controller. So what we can see is that actually what we're going to do in the first state is we're going to run it a number of times, and for this example I've decided to run 5 times. The reason for that is in the baseline code the number of epochs is 5. Okay, so I've reflected that. Okay. So the first thing that I wanted to do was run 5 times and reduce the epochs to 1 and remove the random shuffle which reorders the data. Okay, so one would imagine this is now meant to be deterministic, but it isn't. So the first thing that we want to do, although that variation is fairly small, it is still there and it is a concern. First thing we want to do is look at our experiment cases, our constant values, which have a constant value and they have no number range and no gradient, and then essentially our linear ramp, which will introduce number range with a fixed gradient, and then the sinusoids, which will have a number range and a changing gradient. This is some of the code there. It's better in the document. Okay, so With the fixed results, green, by the way, is the highest score. Ran a couple of tests. First thing it seemed logical to do was to run with the value 1. Because when we look at the straight line graphs that's in every little node in there, it's a multiply. So multiplied by 1 would be minimal effect. So that would seem the logical thing to do. However, what we find is that the accuracy is very poor. These are ratios, not percentages, so that's 10.1. Okay, if you just move the decimal place close. Okay, so that was actually 87% worse than the baseline using the random values. So that doesn't look very promising. Next thing was to do was, let's try 0. Probably not a great thing to do, but we'll try that. And it's a similar value and a similar loss, actually slightly worse. These two values here are deduced from going into the Keras code and having a look at the random number and seeing the range that it runs by. And the value that range that it runs by is 0.05 to minus 0.05. So we'll test each side of that number range. And it slightly improves, but it's still not really very newsworthy. So constant values is not looking very great with this model. Try the linear ramps. Taking our minus 0.5 and our plus 0.5 ramp range. Wow, only 2% difference. Okay, so around about 95 instead of 97%, which the baseline has. So this looks promising. We'll try a few other values here because we're interested in the number range here, so we're varying the number range. So in the first value, we've effectively gone from minus 0.05. What we're going to do is slide it up into just positive values, because in that code, one of the layers is a ReLU. The ReLUs, the negative numbers, can have an effect. So the first thing we will do is try it with positive values, with the same gradient. Okay? It's still promising, but it's not as good. Okay? Next thing we want to do is maybe just try reciprocal of that to be complete, which just slide it down into the negative number elements. Similar. And then the last thing we do is we try the other one, and we're back to that very bad condition again. Okay. So that was the linear ramp. So our linear ramp between the Keras random number limits using a linear ramp has comparable performance. Okay. So let's try the sinusoids. Now I was very surprised at this because I was actually intuitively I had thought that a change in the gradient might assist gradient descent perhaps during its learning mechanism. Actually it's very similar score. We'll come back to perfecting these values when we overcome this random variation in a minute, and we'll score which is the best in a minute. And try the other experiments again. These are also very similar with the previous experiment, which was really just doing number range, not changing the gradient. Okay. So out of the highest scores of our 3 experiments, the best ones that we had, there was the rather poor constant value, the linear ramp between minus 0.5 to 0.45, and the sinusoidal within the same range. Okay. So these are what the actual tensor looks like plotted out in the initial weight states. Okay. But we still have this run-to-run variance, and in order to be able to deduce whether it's the linear ramp or the sinusoid, even to a small degree, we're going to have to resolve this run-to-run problem. First thing that was essentially run it back at the 5 epochs, so it's exactly comparable with the baseline. Okay, so these are the values run with the sinusoid, which we're assuming at this point is the best score, and then comparison with the original code. This is not in the paper, but, and it's not strong enough perhaps to put in the paper, but I might look at it for the extended paper for the journal, is I will point out that the variance in the values when we're using non-random structures is less than it is in the original case. I only noticed that when I did the slides. Okay, so two theories could be that we're having a numerical representation problem. One, the use of the softmax, because we're dividing by the sum of a value. We can imagine that there's a representation issue that might occur. And the other one is a little bit more esoteric. And that's in an Intel processor, that's what I'm using, there's an 80-bit extended precision register, which is internal. And every time the scheduler comes in, it will get truncated. And the scheduler's event is effectively random. That's a possibility of this rounding could be occurring, causing the variation. So, looked at this, and there is some code to be able to set your Python task into a real-time priority with an affinity of one processor, okay? So that it's non-interrupted. The caution on that is you must run your Python task in administrator mode such that it actually does select high priority, otherwise it won't tell you, but it will set it to high priority instead, and you will get the variation continuing. So what essentially happens then is, wow, that looks very hopeful. Now we get in every learning session exactly the same value. So now we're in the case where we can do that evaluation between a sinusoid and a linear ramp. So the highest score sinusoid and the highest score linear ramp, and in a graph here, I've just put them here, this is percentages. And we can see that actually the linear ramp is slightly better than the sinusoid. So number range is important rather than changing gradient. For completeness, because the softmax has been identified as a possible concern, either pre and post scaling, we got a very marginal, very small increase in accuracy. So it wasn't obviously the major contributor. So it does look like it's our scheduler issue. And then we can, if we compare that, because now we can get a very accurate measurement for the original code, although seeded, we now have a value index to be able to measure the differences between them. So essentially the results are this. With the random number scheme, which is our top score, along that is the linear ramp, and it is only 0.18% less, showing it is very comparable, i.e. random numbers are not an imperative requirement. The sinusoid, and sorry, with the softmax removed, is 0.21 less. Okay, so there's a marginal effect that's happening with with the summation in that softmax function, and the sinusoid is about 0.33% difference. So this paper therefore has demonstrated that random number schemes are not an imperative requirement. In fact, if we consider that variance, which still needs to be looked into, it could be that random numbers actually introduce unintentional colorization when you consider those random numbers coming from the image, as well as the image, and the initial state. And during that initial part of learning, there could actually be a colorization occurring. And so it appears that the benefit comes from the number range rather than the gradient. And what we should do is caveat this, that other non-random schemes may exist, and that this is coupled to the test case that we tried, okay? And therefore, it may well be test case to the ReLU, the softmax, and the layers that have been used. So we can imagine ultimately that random number schemes, or non-random number schemes, may well be selected on the basis of these. And the numerical instability problem has been resolved, and we can get complete deterministic and repeatable results.
Thank you. So, questions? Yeah.
Yeah. You mentioned that you use modified softmax activation.
Yeah.
What did it look like You know, the normal, I know what softmax is, but did you use random or anything else?
No, it's only the implementation that's changed. So instead of it being divided by a sum, it is pre-scaled and post-scales the number. So it's just a numeric change to preserve the number resolution. Interestingly enough, the work that goes on beyond this in the next paper, we're getting to losses of 7.5 to the minus 5. Minus 5 is quite an interesting number when you consider 32-bit numbers. If you get 5 decimal places difference between them, you start losing resolution. Okay, so we're starting to get to the limits of the representation, which is quite nice.
Yeah, I have to go and meet a new guest in 30 seconds, so I will combine 2 questions in one. First is, many thanks for this very good presentation and topic. First, do you think running it for more than 5 runs? I guess runs you mean epochs.
No, training 5 times
Training
with the same data set. Yeah.
Okay.
Yeah.
But over
Learning
how many-
sessions.
Okay. Do you think if you run for more epochs might make a difference?
Ultimately, my idea is to try and reduce data set sizes.
Yes.
So what we could say is in that first part, it is suboptimal. Those random numbers may in fact be causing colorizations and make the first part of the training suboptimal.
Okay. Thanks. And the other question is general. What kind of application are you thinking about once you feel comfortable with establishing the concept and proving it to move into where reliability and reproducibility of the neural network outcomes is important?
So the area that I work in is threat analysis, and we deal with limited amounts of information.
Yes.
And often we're dealing with uncertainty. The motivation behind this is to take data that we do know, train a network, and then extract the rules to see if they check with our understanding. The other part of this PhD has an expert system which grades multiple hypotheses together in order to value or put a grading on those. This part is envisaged to be the part that might enable that expert system to learn.
Thank you.
So, any more questions? Okay, right. I have listened.
A short question. You talk about the data and training using the data.
Yeah.
How about cross-validation? Means using different part of the data each time you train.
Okay. So with the demonstration, it is using cross-validation because that's what comes in that test. There is a validation set, there's a training set, and there is a set. What we're not doing though in this particular work here is setting the hyperparameters using the training sets, because the code from the baseline is seen as being perfect. With the work that we're doing beyond that, we're looking at learning rate particularly, and the coupling of learning rate and the number of nodes. And in the paper that will be produced, what we do find is they get tradable. But ultimately what we want to do is reduce data set sizes to take understanding quicker.
I understand, but you run your code 5 times, you
Yeah.
presented result for 5 times. I'm saying if you generate results that 5 times with the same data set but different part of the data set, how the result will look like?
So I imagine that I will get a variation and a variation in that training. With the subsequent work, that's something I'll have to look at. With this work, I just executed the code as is because I didn't want to modify the baseline code because too much, because it's verified.
Okay.
Okay.
Yeah. Just one question.
Or the training scheme.
You didn't mention the data size you are using for this training, and then what the batch size do you have any variance in batch sizes as well for training?
No, I haven't. Again, in this case, it's a like-by-like comparison. So the validated implementation is what we're using. With the work that I'm doing for the rule extraction, yes, I am looking at that because I want to be able to get answers more precisely with